Okay, let's look at a couple of examples of natural response in RL circuits. And we'll first start with something that looks kind of similar to what we were looking at earlier for our very first example, except now we've made our resistor network a little more interesting. But once again, we have a switch that's closed. It will open at t equals 0. We want to find IL, the current through the inductor, and VR, the voltage across that 40 ohm resistor for t greater than or equal to 0, assuming steady state for t less than 0. So how do we work this problem? Well, even if we weren't asked for IL, we would have to find IL. So IL must be found first. IL of t will be equal to the initial condition times e to the minus r over L times t. We need to find the initial condition for t less than 0 and the value of r for t greater than 0 before and after the switching event. So for t less than 0, we find the initial condition. Once again, the voltage across this capacitor will be equal to 0 volts. And in this case, looking at this, if I've got 0 volts and this switch, of course, is closed, then I've got 0 volts across this resistor. I've also got 0 volts across this entire resistor network here. So I've also got 0 volts across those 3 resistors. And if you combine them all together and they have 0 volts across them, then that means all the currents are going to be 0 through all those resistors. So in this case, I know that I have the only possible place, the only possible path for current, since this is 0 and since this is 0, the only possible path is for this 20 amps to be flowing through the inductor by Kcl. It's only got one way to go. And so therefore, IL just before the switching event is equal to IL just after the switching event is equal to our initial condition, which is equal to 20 amps. All right. So now we note, incidentally, just want to note here that VR for t less than 0 is equal to 0 volts. Since there's no current flowing through any of these, since there's no voltage across this network of resistors, then VR must be equal to 0 as well. Now I just kind of bring that up to show that this is why I can't apply that solution to VR. It's not going to work. I'd be starting off with what looked like a 0 initial condition. The voltage across the resistor is not going to persist across the switching event, but the current through the inductor will. Okay, now let's find the equivalent resistance for t greater than 0. So for t greater than 0, let's find R. And so in this case, the switch is going to open. Now, all of the current through the 20 amp resistor, or pardon me, the 20 amp source is going to flow through the 0.1 ohm resistor. So this current is no longer going to have any effect on this side. I've got an open connection between these two nodes. So everything that's going to happen is going to happen between this inductor and these resistors on the other side, because I know that the current through here has got to be 0 just by Kcl. So given this, what is the resistance across this inductor? Well, in this case, what I'm going to have is that the resistance across that inductor must be the resistance between these 2 points across the inductor. That's my R. In this case, R must be equal to 10 in parallel with 40 plus 2. So if I do resistor network reduction and go through, combine the two parallels, add the series resistor, and then what I'm going to get is this is equal to 10 ohms. And in that case, tau is equal to L over R, which is equal to 2 divided by 10 is equal to 0.2 seconds. And now I take this, plug that in, and what I'm going to get is that IL of t will be equal to 20 times e to the minus 5t amps for t greater than or equal to 0. And there's our solution for I of L. So this is straightforward. We find the initial condition. We find tau, in this case L over R, take the inverse, plug it into the equation, and there's our result. Now we need to find VR. Okay, that's a little bit trickier. We can't apply the general solution because we would just get 0. So that does us no good. That's why I did this earlier to show that I can't do the general solution. But I now know what IL is equal to. So in this case, I know that IL is equal to 20 times e to the minus 5t amps. That's the current flowing through that branch. So what I'm going to do is I'm going to ground this. This is VR at this node. And now I'm just going to say, well, this current IL must also be the current flowing through that 2 ohm resistor. And now I'm going to write a Kcl equation. And what my Kcl equation says is that 20 times e to the minus 5t, this current, plus VR over 10, this current, plus VR over 40 is equal to 0. So I just wrote a Kcl equation for that node. I can now solve this by hand, and what I will get is that VR of t will be equal to minus 160 times e to the minus 5t volts for t greater than 0. And there's my result. So there's my current, there's my voltage, and in this case, I got the voltage across this resistor from the current equation that I'd already solved for I of L. That's how you have to work these problems. You start with I sub L, and then once you solve that, you can solve for anything else in the circuit just by using KVL, KCL, or any other of the equations you've already learned. All right, incidentally, if we plotted this, if we plotted VR, what would we see? Well, actually, let's plot IL and VR. So IL of t will look like this. So for t less than 0, it'll be 20 amps. At t equals 0, we have a switching event, and then this decays away in 5 tau. For my VR, I'll get this. I'll get a value that was equal to 0 for t less than 0, and then suddenly spikes down to minus 160 volts, and then once again decays away in 5 tau. So in this case, the voltage across the resistor can have a discontinuity. That's why we can't use a general solution on things like voltages across resistors or currents through them, because you can't guarantee the voltage, that the current or voltage won't change across a switching event. But you can guarantee it for the inductor, and that's the difference. All right? Let's look at another example here, and now let's do something a bit different. So far, all of our time constants have been easy to calculate because they've just been networks of resistors. But what if you had an example that had a dependent source? Let's look at that. So here we have a current-controlled voltage source controlled by this current I2 through a 2 ohm resistor. I've got a 0.2 Henry inductor, current I sub L, 5 ohm resistor, 2 amp source, and in this case I have a switch that is open but closes at t equals 0 seconds. So a little bit different for this one. And in this case, I want to find IL and I2, both of those currents, for t greater than or equal to 0. Once again, assuming steady state operation for t less than 0. So once again, either we have to be told to assume steady state or we have to be told the initial condition, one or the other. So in this case, we're assuming steady state, which means once again, we're going to assume that the voltage across the inductor is equal to 0. All right, so what do we have here? Let's go through and calculate this. Once again, we must start by finding I sub L. So find this first. Then we're going to find I2. So for t less than 0, let's find the initial condition. Find I0. So in this case, I'm going to ground this. If I ground this node, and I know that I've got 0 volts across my inductor, then that means I've got 0 volts at that node. So this is not really a defined node, but we know what the voltage has to be. So that's useful to us. Now let's go through, and this switch is open. It has no effect on the circuit right now. So in this case, what we'll find is I've got 2 amps. I'll also have that same 2 amps is going to flow through that resistor. And in this case over here, I'm going to have a constrained, or rather a defined node with a value of 3I2 at that node there. Okay? So I filled in all the gaps. Let's go through, and in this case, the directions of the currents are already very apparent, so I can go ahead and write my Kcl equations. And so what I get here is, well, looking at this, I'm going to write my dependent source variable equation first. Let's go ahead and do that. So my DSV says that 0 minus 3I2 divided by 2 must be equal to I2. So just using Ohm's law to define I2. And if I solve for this, what I'm going to get is that I2 is equal to 0. So in other words, the only way that 2I2 can be equal to minus 3I2 is if I2 is equal to 0. So that's what I get for I2. All right? Now I'm going to write my Kcl equation. I'm going to write it at this node. 2 amps is equal to IL plus I2, except I2 is equal to 0. I already know that. If that current's equal to 0, I've got 2 amps entering this. The only place it can go is through the inductor. And therefore, IL is equal to 2 amps for t less than 0, and therefore I0 is equal to 2 amps. The initial condition is 2 amps. I know that initial condition is going to persist across any switching event. All right? Now let's look at what happens to the circuit after the switching event. And this is an interesting thing. So let me go ahead and write my initial condition. I'm going to put it up here. So I0 is 2 amps. So I'm going to keep that there so I don't forget about it. And now I'm going to close the wire at t equals 0. Now, watch this, because a lot of people have some trouble grasping what's going on with this. I've now got a wire across this current source. Let me show you a little topological trick. If I got one wire from this point to this point, couldn't I just draw a second wire next to it? I mean, after all, since this is all the same node, does it matter if I draw a second wire connecting the top and the bottom? It doesn't change anything. Couldn't I then erase that little bit right there? Once again, this is all still the same node, top and bottom. But now look how I've drawn it. I've drawn it in such a way that now you can see for yourself that the only place that 2 amps is going to go is through that short circuit wire. It's just going to circle, it's just simply going to circulate in that wire that's across the 2 amp source. It will have no effect upon the rest of the circuit. So I've got 0 volts here. So that's what I've got now for t greater than 0. So let's go through here and we'll erase some of these. Okay. So in this case, I now need to find, for t greater than 0, I now need to find R across L or RTH across L. Thevenin resistance across there. Okay, so I want to know the Thevenin resistance across this inductor. I want to know the Thevenin resistance between those 2 points. There's only one problem here. Now I have got a dependent source. I can't just add resistors together. So in this case, I have to go through and apply the source driving technique. All right? So let's apply source driving to this. Noting over here this current has no effect. If you want, you can zero out that source. It's not going to do anything to the circuit. So, I mean, I can go ahead and just do this and say, if I'm going to use Thevenin's theorem, that zeroes out, has no effect on what I'm going to do over here. So I'm going to do the normal technique. I'm going to add a 1 amp source. I'm going to find VT. So what's VT here? I'll define a current. I note that I've got 0 volts because this is all ground going around here. And so therefore, 1 amp going in must be equal to VT over 5 plus VT minus 3I2 divided by 2. I2 is equal to VT minus 3I2 over 2. So that's my dependent source variable. That's my Kcl equation. And now I can go through and solve, and what I will get is that VT is equal to 2.5 volts, and therefore our TH is equal to VT over 1 amp is equal to 2.5 ohms. This is no different than the source driving technique we're already aware of. We've already seen this. This is just a Thevenin resistance. That's all that R is. It's a Thevenin resistance across the inductor. And so therefore, in this case, what we have is that IL of t will therefore be equal to my initial condition, 2 times e to the minus r over L, 2.5 divided by 0.2 times t is equal to 2 times e to the minus 12.5 t amps for t greater than or equal to 0. So there's my equation for IL. Now I want to find I2. What's I2 going to be equal to? I want to go ahead and put my inductor back in. So I've got VL, IL. I've got an expression for IL. I know what that is equal to. That's equal to 2 times e to the minus 12.5 amps, 12.5 t amps, excuse me. Okay, and so in this case, a couple of different ways I could work this. In this case, I'm just going to go ahead and say, hey, if I know what VL is, I'm just going to use Ohm's law. And VL is equal to L times DIL dt. I'm just going to use the IL expression, find VL directly. That's equal to 0.2 times minus 25 times e to the minus 12.5 t, which will be equal to minus 5 times e to the minus 12.5 t volts. So that's VL, and therefore from here, what I get is that I2 is therefore equal to VL minus 3I2 divided by 2. Do a little bit of algebra to this, and what I will get is that I2 is equal to VL divided by 5 once I simplify terms. And therefore, this is equal to minus e to the minus 12.5 t amps for t greater than 0. And there's our result. So once again, always be sure to find IL first. Any other voltage or current you need to find afterwards, you then calculate once you know what IL is. And there's your result. Okay? So we now looked at examples for RL and RC circuits, natural response. So what we're going to do now is we're going to move on to the next step. We've looked at natural response where we have a source and we set an element to an initial condition and take the source away. Now we're going to look at situations where we start off with a 0 initial condition and add a source, and then see what happens as the inductor or capacitor charges up, absorbs energy. So we'll look at that next time.